Next up is multiple regression. We already talked about linear regression, and linear regression is simply using a model to predict one variable from another. Multiple regression, we're still going to use a model, except this time we're going to predict some type of outcome from several different types of predictors. So multiple regression as an equation, simply just a relationship between multiple variables. All it is a variation of the equation that we use for a straight line. So in linear regression, right, we had y is equal to a constant plus b1 x1. Here we're just going to add more coefficients to go with each variable. As such, and then usually sometimes there's always an error term, but with statistical models we don't have to have that error term in there. So when we look at the three different types of the sum of squares, the total sum of squares is just that difference between the observed values that we have and the outcome value. R is the difference between the predicted and the observed values. So when you think of SSR, R stands for residual again, and a residual means the error. So what's the difference between the observed values and the predicted? That is the error, right? The error in the model. And then the SSM is simply between the predicted by the model and the mean value. So that is the adequacy of the model itself. Alright, correlation coefficient. We talked about that with correlation as well as linear regression. The bad news is it no longer makes sense to look at this. Instead, what we need to do is look at this multiple regression coefficient, or really called our multiple correlational coefficient. So that's the correlation between the observed values and the predicted values. Very similar to the simple correlation coefficient, we have large values, and those large values represent a large correlation. Or a very strong correlation. And this multiple regression is really just a gauge for us, and it's going to tell us how well this model actually is good at predicting the observed value. Alright, sorry about that, I didn't mean to go that quickly. So that multiple R is very useful for us, very similar to the correlation that we talked about, as well as the simple regression. But what we really want to know is this multiple R squared, which is the exact same thing as it was before. That tells us the amount of variation. Alright, so that's the amount of variation that is in the model. So you could take the R value, you square it, that's what we end up with. So that is really telling us how much is in our model and how much we're actually missing in our model, right? And that's really going to be very helpful for us in the future. Now, in terms of predictor variable, so with multiple regression, we're going to have multiple regression coefficients, multiple variables, and the question always comes into play is, well, how do we take these variables and actually put them into the model? So there's a lot of things that we can do to try to figure out how we're going to enter these values in the model. And we're going to use those regression coefficients to determine that. So let's say we've got 5 regression variables, we've got 5 regression coefficients. We're going to look at those regression coefficients and then use that information to input those into the model. Unless you have some type of past information or past research that is telling you that 2 out of those 5 have been shown in the past to be able to predict your outcome variable well. So those would obviously get put into the model first, followed by the ones that are unknown. Or you could have some theoretical value, which is forcing you to put certain variables into the equation at a certain period of time. But the one thing that we absolutely do not want to do particularly, SPSS and any other statistical software package makes this pretty easy for you. You don't want to select all the variables and just throw them into the model. That's going to give you a very poor model result, and that's really not what we're looking for. So let's just see and use our regression coefficients. We have the capability to get that information, so we'll use that to be able to put the variables in the model. Now, what we would prefer is that all of our predictors to be uncorrelated. Because if there's no correlation, then they're each going to contribute to a portion of the model. And if they're all uncorrelated, for those that are remaining, again, anything that's past research you've already put into the model. Anything that's remaining, the order of the entry will have little effect on the outcome. Now, if there is correlation present between the predictor variables, everything is very, very critical. Okay, and we're going to spend some time talking about how we put these elements into the model itself. And that's actually our next conversation. There's 3 methods: hierarchical, forced entry, and stepwise. And we're going to go over the 3 of these. And we're going to learn which ones we should probably go with. So hierarchical, that's where you have past research. Right, so you know you have past research, and you're going to put those into the models first. Now, when it gets to running this on SPSS, this is going to seem very odd, because within hierarchical, you could use forced entry or stepwise. Because of the first order of importance, we have the variables that are predicting the outcome known from past research. We're going to actually force all of those predictors into the model first. And then the new predictors could be entered stepwise, or you could force them in, or you could create multiple blocks. So block 1 would be our known predictors, and you could have block 2 through 20 if you wanted, for hierarchicals. What is really nice about the hierarchical approach is that the researcher actually gets to make the decision. So you as the researcher would have the most information, and the most inside information, I should say, about how this project is going forward, so you should know which goes in first and which should go in last. And you can also use your correlation coefficients to kind of assist you in that method. So hierarchical, what's the greatest thing about it? It is indeed the best method to use. You're using it because you have past information, and you can see very, very uniquely the influence of each individual variable on the outcome. But there is a bad point. Researcher has to know what they're doing, or the experimenter has to know what they're doing. If they don't know what they're doing, they could get a really crappy model out of this, and or a very inaccurate model, which would be even worse. So that's the only bad point for hierarchical regression. There's bad points with the other models, with the other methods too. Forced entry. If you're going to force something into the model, which is why it's called forced entry, you should probably have a good theoretical rationale, like we discussed in the hierarchical method. Again, I said in that hierarchical method, block 1, if you have previous known information, which is based upon good theoretical rationale, you're going to force the variables into the model. What does forcing the variables into the model mean? You've got 2 variables, and you are forcing 2 variables in the model. Your model will have 2 variables, even if one of those variables turns out to be poor. So you're forcing them both into the model. Forced entry can be really a better method. If you want to test some theories. So maybe you've got some preliminary data, and before you go out and collect a whole bunch more data, you want to make sure that the data that you collected is worthwhile to collect. So I'm going to collect data upon how you make decisions when you go to a fast food restaurant, and we're going to base it upon whether it's sunny or cloudy or rainy outside. So you collect all this information and you throw it in the forced regression model, and it turns out that weather has no impact on how you select food at a fast food restaurant. However, gender and time of day are very highly correlated. So now you know you don't have to collect information on the weather conditions for that particular study. And so the reason for when you're just testing theories is you're probably not going to have replicatable results, because your data is going to be changing as you're collecting more information, because you're just simply testing theories out. Okay, so now moving on to stepwise regression. Stepwise regression is probably a method that you guys will like a little bit better. So now we're going to enter the variables into our model based upon some type of mathematical criteria. When you're using SPSS, that mathematical criteria is going to be your regression coefficients. So SPSS, you can say, hey, I have all these 10 variables, not sure about them, I want them all entered in the model stepwise. And then SPSS will decide which variables should be entered when, and it will only keep those that are in the model that are actually improving the prediction of the outcome variable. So there's a couple methods to do this. The first method is the forward method. And when we have that, we have an initial model. And it only has B0, which is our constant. All right, and then the computer is going to select predictor variables. Right, so whichever variable has the highest simple correlation, that's what they're going to put into the model. And if, and only if, the predictor improves the model, will the predictor be retained? All right, and then the computer searches for next best. And that's probably going to be the variable that has semi-partial correlation with the outcome, right? So why semi-partial correlation? Again, partial correlation is measuring the relationship between variables, controlling for the third. And semi is measuring the relationship between the two variables, measuring for the effect the third has only on one of the others. So that one of the others is the outcome variable, and we're really going to focus on the semi-partial correlation. So in regression, we're measuring that relationship between a predictor and the outcome. And we're going to have to control for the predictor that's already in the model. So what's really nice about this is in the semi-partial correlation for multiple regression, we are really getting the unique correlation or the unique contribution of that particular new variable in the model. And that is exactly what we want. We want the predictor that has the most impact on the outcome to be added to the model next. So let's say we have the first predictor explains 40% of the variation in the outcome variable. Alright, we've got 60% left, right? So the computer is going to search, or SPSS, it's going to search for the largest part of 60%. And that's going to leave us with how much the new variation can be explained. And obviously we would really like to do this until we get to 100%. But there's always times that we're never going to be able to collect all of the data that's in a model, and we just simply might not be able to predict very well, or we might not know what those other variables are. So stepwise regression also has a removal test in the forward method. So after it's included the least useful predictor, what SPSS will do, it's going to regress this equation and reassess it to see if we can remove and so if you remove these predictors, does it improve the model? So that's what it does. It goes through this forward, it adds, it adds, it adds, it adds, it adds, and it takes away that last useful predictor just to verify which of those two models was best. The one with the useful predictor, useless predictor, or the one without it. And then it will produce the ultimate decision in terms of what model you should use. Now there's the next method, backward method. Obviously it is the opposite of the forward method. So what does that mean? we start with a model that has all of the predictors entered into it. And then the computer is going to calculate the contribution by each predictor. And it's looking at that by a t-test. So if the predictor's not making a significant contribution, the predictor's removed. And then it reassesses the model for the remaining predictors. So at least now you have two ways of stepwise regression to go with. They each have their pros and cons. But let's look at an example of what we should do. So we've got an exam mark, and we've got first year grade, difficulty of question, and time to revise. So when we just look at the correlation, we have revision time is obviously what is predicting your exam score pretty heavily, right? And then the first year exam grade and difficulty of question are each contributing about the same. So if you had a choice here, which one do you put in first? I would put in revision time in block 1, and then in block 2 I would do exam grade and difficulty questions, put them in there simultaneously, and let SPSS do a stepwise regression for those two. Alright, so of those stepwise regression, which one is best? Most people prefer the backward method because of suppressor effects. And what are suppressor effects? Well, it occurs when we have a predictor that has a significant effect, but only if another variable is present in the model. Alright, so that is really the best thing. Now the forward method is most likely to exclude predictors, which obviously increases our type 2 error. You really don't want to do that. And you could miss a predictor. So regardless, either the backward or the forward are perfectly acceptable to use, understanding that the issues that you have with each. The biggest thing to understand about stepwise regression really taking the decision out of the hand of the researcher or the experimenter. However, if you combine stepwise with hierarchical and or forced, what you can do, you're reducing the issues that we have with stepwise regression. Another problem, if you're just throwing the numbers in, you could end up with including a predictor that goes against your theoretical decisions. You could also overfit a model. What does overfitting mean? You have too many variables and some of them make very little contribution. You could also underfit a model, right? Now you're leaving out predictors. So stepwise has a lot of pros and cons with it, but the best thing to do go ahead and avoid stepwise regression. So we just had a really nice conversation about it, and I just said just to avoid it. Unless you're exploring your data. If you are trying to approve a model that has already been developed, and you know you have a couple predictors that are very valuable, you're going to force those two predictors in your first hierarchical block. And then you're trying to improve the model because the model maybe it only had 40% explained variance. You're trying to find out what's the other 60%. If you're trying to find out what that other 60% is, you're going to use the stepwise regression to explore all of those predictors. Now, stepwise regression could also be used if you're splitting your data set and you're trying to cross-validate your model by coming up with two models that are very similar to each other by splitting your data set. But again, that's more advanced regression. We're not going to cover that in this course. But again, most of the time we are trying to explore new ways to improve models. In that case, stepwise regression is perfectly acceptable. Next question that comes into our regression model is, how accurate is our model? Does the model actually fit the observed data? Or do we have just a few cases that are influencing the entire model? And we create regression models because we have a set of data and we want to generalize that to the population. Maybe we also want to generalize that to other samples. So these are the questions that we're going to try to answer here in the next upcoming few minutes. All right, so does the model fit the data? Well, do we have outliers, right? Sometimes those are called residuals. Do we have outliers? And we're going to be able to look at some standardized residuals to figure that out. And do we have cases that are influential? So they're not necessarily outliers, but they're simply having a pretty big impact on the model itself. To find out if we have influential cases, we're going to look at Cook's distance. And both of these things are generated through SPSS. All we need to do is evaluate what they mean. Okay, so for the outliers, again, what are outliers? They're data points that are differing substantially from the main trend of the data. And when that happens, we're going to end up with a model that's biased. And this is going to end up affecting our regression coefficient values. So that's really going to impact the model. So what happens with an outlier? So when we have the presence of an outlier, we end up with our regression slope that becomes flatter, and our intercept increases. So when you look at the graph below, we've got an outlier that's down here, so our model is going to get flatter and the intercept will increase, which means we're going to have a smaller regression coefficient. Now those residuals, that's our error value, right? The difference between our outcome predicted and our outcome observed. We can either have small residuals or we can have large residuals. This is the error value. If we have small residuals, we probably have a good model. If we have a large amount of error, we're obviously going to have a poor model. Now the problem is, in just looking at residuals, we can't look at the residuals and compare against a bunch of different models, because these residuals are what we would call unstandardized. So what we need to do is we're going to have to standardize these residuals. How do we do that? We're going to take those residuals and divide them by their standard deviation. So when we talk about standardized residuals, we want, in an average sample, 95% of those residuals to fall between positive and -2. Remember, we go back to our z-score, and that's kind of similar to that, within 2 standard deviations of the mean. And we also want 99% to fall between positive and -2.5. So now an outlier is going to be any case where we have an absolute value of our standardized residual greater than or equal to 3. Right? If that is the case, we definitely have an outlier, or it's more likely to be an outlier, statistically speaking. All right, what's an influential case? It is one data point or a group of data points that has undue influence. On the parameters of the model. Alright, so how do we know we have an influential case? Deletion of this one data point will result in different regression coefficients. right? Do we want one data point to change our regression coefficients? No. We want a model that is stable, right? Stable across the sample. Because we want to be able to remove one data point and have our regression coefficients not change at all, or change by several hundredths of a decimal. How do we determine whether or not we have an influential case? Well, SPSS is going to provide us a lot of information on this. They're going to actually remove the data point from the analysis, develop a new model, and if we have little influence, the predicted outcome will be similar to the original outcome. And this is what SPSS calls a DF fit. So that is really just the difference between the adjusted predicted and the original predicted. Problem with the DF fit it depends upon our units of measurement, so it's not comparable. So if you want to be able to compare the DF fit values for an entire model, we have a standardized DF fit that SPSS will calculate for us. We can also look at our deleted residuals. That deleted residual is the difference between our adjusted predicted value and the observed original value. Now that deleted residual, again, not comparable, so we create a studentized deleted residual, and that's just that deleted residual divided by the standard deviation. And the reason we're using the studentized, because this is a value that is comparable across different regression models and different regression analyses. The influential case, the problem that we have is we really don't have any information how that one data point influences the model as a whole, and our model's ability to predict all cases. So we're still not there yet, but we're getting closer. So the next thing that SPSS will calculate for us is Cook's distance. Now Cook's distance is right what we want to know. Alright, now it is measuring the influence of a single case on the entire model as a whole. So, a Cook's distance, any absolute value that is greater than 1, you should be concerned about. Alright, so at least that's one of the things that we can do looking at influential cases is Cook's distance. We've got a few other things that we also would like to look at, but Cook's distance is one of those things that we want to look at. Something else that we could look at is what we call a DF beta. The difference between a parameter estimated using all the data points and when one data point is excluded. Just like anything else, it's not comparable. So what do we need to do? We need to calculate a standardized DF beta. What do you think we do? We either divide by the standard deviation or the standard error, because that's what everything makes things standardized. So if we have absolute values greater than 1, we have a data point that has substantially influenced the model. So that's another group of data points that you can look at, is that standardized DF beta. Next one is our leverage, or our hat values. This is also a way to gauge the influence. Of our observed outcome versus our predicted outcome. In order to compare our leverage values, we have to calculate our average leverage values. Average leverage values, we take k plus 1 and we divide it by n. K is the number of our predictors, and n is the number of data points. We should have leverage values that are approximately equal to the average value. If we have those that are comparable, right, comparable, close, we don't define how the word close means, but if the leverage values are close to the average leverage value, we don't have any influential cases. So the leverage values is a third one that we can look at. And we've got a fourth one, the Mahalanobis distance. This is really measuring a distance from the data point from the mean value of the predictor. Alright, we're going to start to look for some high values of Mahalanobis distance. What does a high value mean? Well, if you have a large sample size, a high value would be something like 25, so 25 or greater would be a cause for concern. If you've got a small sample size, we're going to be looking at values of 15 are a concern, and a very small sample size, we're looking at values greater than 11 are a concern. So the Mahalanobis distance is number 4 that you can look at. And then the last one is our covariance ratio. So when the ratio is close to 1, that means our data point has no influence. P-O-I-N-T. if our covariance ratio is greater than 1 plus 3 times the number of parameters plus 1 divided by the number of data points, or if it's less than that, we've got two things that we need to worry about. So the covariance ratio greater than that, then deleting the ith data point, so if we remove it, we're going to damage the precision of the model. And if it's less than, deleting that data point, will improve the precision of our model. So the covariance ratio is something else that we want to look at. We certainly don't want to delete it if it's greater than that point, and we would like to delete it if it's less than that. So we do have an influential case. Now it is important to note that just because you have residuals or outliers or influential cases, it's not justifying just removal of the data points to improve your model. So as a general rule, let's say you have an outlier, but Cook's distance is less than 1, don't remove that data point. And most important thing, find out why it doesn't fit the data set. Why is it not fitting the model? What is going on? What happened when that particular data point was collected? Is there something that you should consider? If it does not the same as the sample, if it's a different sample, maybe that data point, now you can justify removal of it. But you have to find out why. You just can't go randomly deleting data points because now you are falsifying your data set, which is usually not a good thing to do.